Hold a single point in your mind. Not a dot on a page, but a point inside a space you have never been told exists. That one point is an entire universe. Every star, every void, every curve of space, the whole shape of a cosmos compressed into one location. Move a fraction in any direction and the galaxies rearrange, the geometry bends, a different universe appears. And a line traced through this space, a thread running from one point to the next, is not a journey from place to place. It is a complete history of a universe, beginning to end, laid out all at once. There is a place where every possible shape that space could ever take already sits, side by side, motionless. One of the most influential physicists of the 20th century believed this place was more fundamental than space and time themselves. He gave it a name. Then he helped write an equation to govern it, an equation so strange that one of the men who built it spent the rest of his life wishing it had never been written, and asked, in the end, for it to be thrown into the dustbin of history. This is Superspace, Wheeler's Superspace, the hidden arena of quantum geometrodynamics, where whole universes are single points and where time somehow disappears. Before the screen goes dark, you will understand what superspace is, why the Wheeler-DeWitt Equation seems to say that nothing ever happens, how the vacuum is balanced to 1 part in 10 to the 120th, and why the man who fathered that master equation called it that damned equation. If you find value in explorations like this, the subscribe button quietly helps these deep dives reach more curious minds. So, here is where it begins. To understand superspace, you have to first give up a habit of thought so deep that most people never notice they hold it. The habit is this. You imagine the universe as a stage, and you imagine things happening on that stage. Space is the floor. Time is the clock on the wall. Stars and galaxies are the actors, moving across the floor while the clock ticks. This picture is so natural that it feels like the only possible picture. It is also, according to the framework we are about to examine, wrong, or at least far too small. John Archibald Wheeler did not think the stage was space. He thought the stage was something larger. In an essay published in Harper's Magazine in 1974, Wheeler wrote it plainly. The arena in which space does its changing is not even the space-time of Einstein, for space-time is the history of space changing with time. The arena must be a larger object, superspace. And then came the line that tells you how far he was willing to go. Superspace, he said, is not endowed with 3 or 4 dimensions, it's endowed with an infinite number of dimensions. Sit with that for a moment, because it is the hinge on which everything else turns. We are used to space having 3 dimensions: length, width, height. Einstein added time as a 4th, weaving them into space-time. Wheeler is telling you that the true arena, the place where the action really happens, has not 3 dimensions, not 4, but infinitely many. To see why a serious physicist would say something that sounds like poetry, we have to be precise about what a single point in superspace actually is. Picture the whole of space at one instant. Not its history, not its future, just space itself, frozen, the way a single frame is frozen out of a film. That frozen slice of space has a shape. It has a geometry. It might be curved here near a star, where mass bends it. It might be flat there, far out in a void. Mathematicians call this complete description of the shape of space at one moment a three-geometry. It is three because space has three dimensions, and geometry because what we are recording is its shape. Every curve, every bend, every distance between every pair of points within it. Now here is the move that builds superspace. Take that entire three-geometry, the full shape of all of space at one instant, and collapse it down to a single point. One point. Not a point in space, a point that is a space. A point that stands for one complete possible shape of an entire universe. Then do it again for a different shape. A universe where the curvature is slightly stronger. Another point. A universe where a galaxy sits a little to the left. Another point. A universe shaped like nothing we have ever seen. Another point. Collect every possible three-geometry that could ever exist. Every conceivable shape of space, and let each one be a single point. The space of all those points is superspace. What does it mean that an entire universe can be a single point? It means that the thing we call the cosmos, all 100 billion galaxies, all the dark distances between them, is, from the vantage of superspace, one location among infinitely many. And the reason superspace has infinitely many dimensions is now almost obvious. To specify the shape of space at a single point, you need three numbers. To specify the shape of an entire three-geometry, you need the curvature at every one of its infinitely many points. Infinitely many independent quantities. Infinitely many dimensions. The arena is not large, it is unlimited. Wheeler's collaborators made this mathematically exact. Superspace is written as the space of all possible geometries of space. You construct it by taking every smooth way of measuring distances on a three-dimensional manifold and then throwing away the differences that are mere relabelings of the same shape. In the notation of the physicist Domenico Giulini, who mapped its structure carefully, superspace is rem of sigma, modulo diff of sigma. Spoken aloud, the space of all Riemannian metrics on a surface sigma divided by the group of diffeomorphisms, the smooth coordinate relabelings of that surface. Rem of sigma is every conceivable way of laying down distances. Dividing by diff of sigma strips out the duplicates, the geometries that look different only because you painted the coordinate grid on differently. What remains after the duplicates are gone is pure shape, the set of genuinely distinct three geometries. That quotient is superspace, and the formula S of sigma equals rem of sigma modulo diff of sigma is its definition. Hold on to one feature of that construction, because we will return to it much later, when the calm of this presentation has given way to something sharper. We divided out the relabelings. We insisted that only the genuine shape matters, not the coordinate grid we drew on top of it. That insistence has a technical name: diffeomorphism invariance, and it is one of the deepest truths in Einstein's theory of gravity. It is also, as we will see, the source of the single most disturbing problem in this entire subject. For now, simply note that it is there. The coordinates do not matter. Only the shape matters. Keep that. This strange arena did not come from idle speculation. It came from a hard, practical problem: how to take Einstein's theory of gravity and rewrite it so that it could be fed into the machinery of quantum mechanics. And that problem has names and dates and a specific room where it was argued. In the 1950s, general relativity was, oddly, a backwater. Einstein's masterpiece sat admired but isolated, disconnected from the explosive progress in quantum physics. The equations were notoriously hard to solve, and worse, they were written in a form that made them almost impossible to combine with the rest of physics. Quantum theory had a particular way of working. You identify a system, you write down its energy, its Hamiltonian, and you let that energy drive the system's evolution forward in time, moment by moment. The trouble is that Einstein's theory does not naturally split the world into space now and time marching forward. It mixes space and time together into a single four-dimensional whole. To quantize gravity, someone had to pull them back apart. Three physicists did exactly that: Richard Arnowit, Stanley Deser, and Charles Meisner, known ever after by their initials ADM, built a reformulation of general relativity across a series of papers from 1959 to 1962. Their reformulation sliced four-dimensional spacetime back into a stack of three-dimensional moments. Picture a loaf of bread. The whole loaf is spacetime, all of history, past and future, as one solid four-dimensional block. The ADM formalism slices the loaf into individual pieces, each slice a complete three-dimensional space at one instant. Stack the slices back up in order, and you recover the history. This slicing is called a foliation. The two quantities that describe how the slices are stacked are called the lapse and the shift. The lapse tells you how much time passes between one slice and the next, the local rate of time. The shift tells you how the coordinate grid drags sideways from slice to slice. Together, lapse and shift tell you how to reassemble the loaf. The motivation of Arnowit, Deser, and Meisner was concrete, and historians have traced it carefully. They were working in the shadow of quantum electrodynamics, the spectacularly successful quantum theory of light and electrons, and they wanted to do for gravity what had been done for electromagnetism. They wanted to strip away the unphysical mathematical baggage and isolate the true physical degrees of freedom, the parts of the gravitational field that genuinely carry energy and radiation. As the historians Bloom, Rickles, and Thébault document, ADM wanted to replicate the methods of quantum electrodynamics in quantum gravity. It worked beautifully in a simplified, linearized version of the theory. In the full, nonlinear theory, the real Einstein equations, in all their tangled glory, they found themselves unable to carry it through. The machinery jammed. But the reformulation itself, the 3+1 split, the foliation of space-time into space evolving through time, survived as one of the most important tools in all of physics. We will see it vindicated decades later in one of the most precise measurements ever made. And it was Wheeler who saw what the ADM reformulation made possible. Once you have rewritten gravity as the geometry of space changing from slice to slice, you can ask a new kind of question. Not how this particular universe evolves, but what is the space of all the shapes that space could pass through? The slices are 3 geometries. The 3 geometries are points in superspace. And the history of a universe, the stack of slices, the whole loaf, becomes a single curve, a single path traced through superspace from one geometry to the next. What does it mean that an entire space-time, all of cosmic history, is just one line through this arena? It means that to do physics in superspace is not to watch a universe evolve. It is to ask which paths through the space of all possible geometries a real universe is permitted to take. This was Wheeler's grand vision, and he gave it a grand program: Geometrodynamics. The dream was breathtaking in its ambition, to reduce all of physics to pure geometry. Wheeler's slogans capture it: mass without mass, charge without charge, field without field. The idea was that a particle need not be a foreign object sitting inside space. It could be a knot in the geometry of space itself, a region where the curvature twists back on itself. Wheeler imagined geons, bundles of gravitational or electromagnetic energy held together by their own gravity. He imagined wormholes, handles connecting distant regions of space. Charge appearing as nothing more than lines of electric field threading through the handle. And at the smallest scale, he imagined that space itself, examined closely enough, would dissolve into a writhing, foaming chaos, the quantum foam, where the very distinction between here and there breaks down. That smallest scale has a name and a size. The scale where the quantum foam is expected to dominate is the Planck length, roughly 1.6 times 10 to the minus 35 meters. Written in more familiar units, it is about 6.3 times 10 to the minus 34 inches, a distance so small that the comparison to anything human is meaningless. Suppose you magnified a single atom to the size of the entire observable universe. The Planck length, at that same magnification, would still be smaller than an average tree. This is the scale at which Wheeler believed smooth space gives way to foam, and at which the calm geometry of Einstein must surrender to the uncertainty of the quantum. To probe that domain, Wheeler and a younger colleague pursued the central question. If a universe is a point in superspace, and a history is a path, then a quantum universe should not follow one definite path. In quantum mechanics, a particle does not take one trajectory. It is described by a wave function, a spread of possibilities, an amplitude assigned to every option at once. So, a quantum universe should be described by a wave function spread across superspace, an amplitude assigned to every possible shape of space, a wave function of the universe. And there should be an equation that this wave function obeys, the way an electron's wave function obeys the Schrödinger equation. That equation arrived in 1967 in a paper of monumental density published in the journal Physical. Review by Bryce DeWitt, titled Quantum Theory of Gravity 1. The Canonical Theory. It runs from page 1113 to page 1148. 35 pages of unrelenting mathematics, and buried within it is the object that would come to bear two names: the Wheeler-DeWitt Equation. Written compactly, it says h hat psi of h equals 0. Spoken aloud, the Hamiltonian operator, acting on the wave function of the 3 geometry, gives 0. H hat is the super-Hamiltonian, the total energy operator of the gravitational field, built out of the geometry of space and its rate of change, together with whatever matter the universe contains. Psi is the wave function of the universe, defined not over space, but over superspace, an amplitude attached to every possible 3 geometry. And the right-hand side is not some elaborate expression, it is 0. DeWitt himself described the goal that drove him, and it points straight back to the arena we have been building. He wrote that the paper was the direct outcome of conversations with Wheeler, during which one fundamental question kept recurring. What is the structure of the domain manifold for the quantum mechanical state functional? Translated out of the technical register, the question is simply this: what is the shape of the space that the wave function of the universe lives on? The answer was superspace. The Wheeler-DeWitt equation is the law that the wave function must obey across that infinite arena. DeWitt called it a cosmic Schrödinger equation, an equation describing, in his words, the whole universe, both atoms and galaxies, in a single mathematical stroke. When the equation debuted, it carried the air of triumph. Here, finally, was a candidate for the Holy Grail, a quantum theory of the entire cosmos, gravity and matter folded into one wave function, obeying one equation over the space of all geometries. The total energy of a closed universe, the equation declared, is exactly 0, balanced perfectly between the positive energy of matter and the negative energy of gravitation. It was elegant, it was universal, it was, to many, beautiful. And yet I want to plant a seed here, quietly, the way the structure of this story demands, and then leave it alone until much later. The man who wrote that equation, the man whose name it bears, would come to regard it not with pride, but with something close to revulsion. He would call it that damned equation. He would say his heart was never really in it. He would ask, decades on, for it to be confined to the dustbin of history. We will return to why. For now, hold the triumph and the unease side by side, And notice that the right-hand side of the master equation of quantum cosmology is 0. Keep that 0 in mind. We will need it. There is a way of seeing where these ideas were forged, and it grounds the abstraction in a real room with real people. In January of 1957, from the 18th to the 23rd, a conference convened at the University of North Carolina at Chapel Hill, organized by Bryce DeWitt and his wife, the physicist Cecile DeWitt Moret. It was, in effect, the meeting that revived general relativity as a living research field. The records list 45 participants, of whom only 10 were based outside the United States, a small gathering by any measure for a subject that would reshape our picture of reality. It was at Chapel Hill that Richard Feynman offered his famous sticky bead argument, a simple thought experiment showing that gravitational waves must carry real energy. The waves could, in principle, do work, heating a bead sliding on a rod as the wave passed. And it was in this same period of intense argument that the idea of many worlds, of a universal wave function that never collapses, was first seriously discussed. The people who built the arena of superspace were not disembodied intellects. They were a few dozen physicists in a room in North Carolina, arguing about whether the universe itself could have a wave function. What does it mean that the foundations of quantum cosmology were laid by so few in so short a time? It means that the picture of reality we are examining, the picture in which the cosmos is one point in an infinite arena, governed by an equation whose right side is 0, is not ancient received wisdom. It is a young idea, barely older than living memory. And as we are about to see, it is an idea still under construction, still contested, and still, at its money, hard, unfinished. Let us go deeper into the arena itself, because superspace is far stranger than the clean phrase, "the space of all geometries," suggests. When you first hear that every shape of space is a point, you naturally imagine something smooth, an endless, gently rolling landscape where you could walk from any geometry to any nearby geometry without obstruction. That picture is wrong, and the way it is wrong matters. The mathematician Arthur Fisher proved that superspace is not, strictly, a smooth manifold at all. It is what is called a stratified manifold, a space made of nested layers, most of it smooth, but pierced by sharp edges and singular points where the smoothness fails. And the places where it fails are not random. They are precisely the geometries with the most symmetry. A highly symmetric shape of space, the perfectly round three-sphere, the most uniform geometry imaginable, does not sit comfortably in the interior of superspace. It sits at a singular edge, at the tip of a kind of cone, a conical singularity in the structure of the arena. Picture the apex of an ice cream cone, or the point of a folded paper fan, where many surfaces meet and crush together into one. The most beautiful, most regular geometries, the ones a calm universe might actually want to occupy, live at exactly the cusps where the mathematics of superspace tears. What does it mean that the most symmetric universe imaginable sits on a knife edge in the space of all universes? It is the first hint that this arena, for all its elegance, does not behave the way a well-mannered space should. To do physics in superspace, though, smoothness is not enough. You need a way to measure distance, a way to say how far one geometry is from another, so you can speak of the length of a path, the straightest route, the dynamics of a universe sliding from shape to shape. Ordinary space has a ruler built into it, and the technical name for that built-in ruler is a metric. Superspace needs its own ruler, and DeWitt supplied one. It is called the DeWitt supermetric, and writing it compactly, it takes the form G with 4 indices, I, J, K, L, equal to 1/2 times the square root of h, multiplied by a particular combination of the 3 metric, HIK times HJL, plus HIL times HJK, minus HIJ times HKL. The details of the indices are not the point. The point is a single, shocking property of this ruler. An ordinary ruler measures only positive distances. Move in any direction and you travel a positive length. The DeWitt supermetric does not. It has what physicists call an indefinite signature, the same kind of signature that space-time itself has, where time counts with the opposite sign to space. Point-wise, the DeWitt supermetric has one negative direction and infinitely many positive directions, one minus and an infinity of pluses. And this means that within the infinite dimensional arena of superspace, there is a single special direction that behaves like time behaves in relativity, a direction with the opposite sign to all the others. The identity of that one special, time-like direction is where intuition fails. You might hope it is time. It is not. This is one of the most subtle and important facts in the whole subject, and it is worth slowing down for. The single negative direction in the DeWitt supermetric is not the flow of time. It is the overall scale of space, the conformal mode, the size, the total volume of the universe. The one direction that stands apart from all the others is the direction in which the universe gets bigger or smaller. Everything else, the infinitely many ways the shape of space can change while keeping its size fixed, counts with the ordinary positive sign. Plant this firmly, because it is a seed that will flower much later into the central crisis of this entire inquiry. The Wheeler-DeWitt equation, built on this supermetric, has the form of a wave equation. And in a wave equation, the direction that carries the opposite sign normally plays the role of time. Here, that direction is not time. It is volume. The mathematics is begging you to treat the size of the universe as if it were a clock. And the question of whether you are allowed to do that, whether the expansion of space can stand in for the passage of time, is exactly the question that, decades later, will bring this entire program to a halt. For now, simply note the strangeness. In the master equation of quantum cosmology, thing that looks like time is not time. It is how big the universe is. The supermetric also lets us write the constraint that lies at the heart of the whole construction. In the ADM formalism, when you slice space-time into moments, Einstein's equations split into two kinds. Some tell you how the geometry evolves from slice to slice. Others are not evolution equations at all. They are constraints, conditions that the geometry on a single slice must satisfy all by itself before any evolution is even considered. The most important of these is the Hamiltonian constraint. Written schematically, it sets a combination of two terms to zero: a kinetic term built from the supermetric and the rate at which the geometry is changing, minus a potential term built from the curvature of the three-geometry itself. Kinetic minus potential equals zero. And when you quantize this constraint, when you replace the classical quantities with quantum operators acting on the wave function, the Hamiltonian constraint becomes the Wheeler-DeWitt equation. H hat psi equals zero. The zero on the right-hand side is not a coincidence or a simplification. It is the quantum echo of a classical constraint, the statement that the total energy of a closed universe must vanish. The zero we were told to remember is forced on us by the very structure of Einstein's theory. There is an old, beautiful result that shows how much information is hidden in pure geometry, and it sits right at the origin of this circle of ideas. In 1962, Ralph Behrlein, David Sharp, and John Wheeler published a paper with a title that reads almost like a riddle: Three-dimensional geometry as carrier of information about time. Their claim was startling. Take two nearby three geometries, two slices, two shapes of space very close to one another in superspace. That pair, they showed, contains enough information to reconstruct the four-dimensional space-time sandwiched between them, including how much time elapsed from one to the next. The time was not given to you separately, it was latent in the geometries themselves. This came to be known as the thin sandwich problem. Two thin slices of geometry and the slab of space-time between them. Think of it like two photographs of a thrown ball, taken a fraction of a second apart. From the two frozen images alone, knowing the laws the ball obeys, you can reconstruct its entire flight and even how much time passed between the snapshots. Wheeler's insight was that space carries time inside its own changing shape. The physicist James York would later refine the mathematics of this problem into a powerful method for setting up the initial state of a gravitational system, the conformal approach that numerical relativists still use today. But here we run into the brutal practical wall of the whole enterprise. The full Wheeler-DeWitt equation, defined over the genuine infinite-dimensional superspace, is, in the words of the technical literature, ill-defined in the general case and far beyond present analytical and numerical capabilities. You cannot solve it. You can barely write it down rigorously. The inner product that would let you extract probabilities is ambiguous. The ordering of the quantum operators is ambiguous. The equation is a magnificent statement that, taken in full, no one knows how to use. So physicists did what physicists always do when faced with an impossible problem. They cheated, carefully. Charles Meisner, the same Meisner of ADM, introduced the strategy called mini-superspace. Instead of the full infinite arena, you freeze all but a handful of the infinitely many ways space can change. You allow the universe to have only a few features, say an overall size, the scale factor, and perhaps a single uniform matter field filling it. You throw away the infinitely many wrinkles and ripples and keep only the smooth, symmetric skeleton. In this drastically truncated mini-superspace, the Wheeler-DeWitt equation collapses from an intractable monster into something you can actually solve, a wave equation in just one or two variables, with the scale factor playing the role of the special time-like direction we discussed. This is where nearly all the concrete results of quantum cosmology come from. And it carries an honest caveat, which the careful practitioners always state. Freezing infinitely many degrees of freedom by hand is an uncontrolled approximation. There is no guarantee that the toy model behaves like the unamazing real thing. We are studying a sketch of the universe, not the universe. Within these mini-superspace models, the most famous questions of quantum cosmology come alive. And here, for the first time, we meet claims that reach beyond pure geometry and brush against the question of why there is a universe at all. I will present them now exactly as their authors present them, plainly, with no verdict attached. The verdict comes later. If the universe has a wave function spread over superspace, then something must fix that wave function, some condition that selects out of all possibilities the actual quantum state of the cosmos. Two proposals dominate. The first is the no-boundary proposal, put forward by James Hartle and Stephen Hawking in 1983. They propose that the wave function of the universe is computed by a particular sum over all compact four-dimensional geometries that have no initial boundary, no edge, no first moment, no starting line. In their construction, asking what happened before the beginning becomes as meaningless as asking what lies south of the South Pole. The geometry simply closes off smoothly, like the rounded bottom of a sphere, using a mathematical device in which time is treated in the calculation as another dimension of space. The proposal favors universes that begin from a single smooth point and expand. The second proposal came a year earlier, in 1982, from Alexander Vilenkin. On his account, the universe tunnels into existence, the way a quantum particle tunnels through a barrier it classically could never cross, from a state he describes as having no classical space or time at all. Vilenkin's wave function keeps only the outgoing modes, the universes expanding away from the origin. The proposals of Hartle-Hawking and Vilenkin are mathematically close cousins. Vilenkin himself has remarked that his proposal differs from the no-boundary one in a certain technical sense, primarily by way of a minus sign. And yet, that minus sign carries them to different predictions, and their authors have disagreed, sometimes sharply, about which is correct. Hold that disagreement lightly for now. We will need it later when we ask what these proposals are really claiming. There is a third great idea that emerged from the same soil, and it concerns not the beginning of the universe, but its very nature as a quantum object. If the wave function of the universe never collapses, if there is no outside observer to collapse it because there is no outside, then every quantum possibility encoded in that wave function, must, in some sense, be real. This is the many worlds interpretation, first proposed in 1957 by Hugh Everett, a student whose advisor was Wheeler himself, and named and championed in 1970 by none other than Bryce DeWitt in an article in Physics Today. DeWitt put the consequence in words that lose none of their force with age. Every quantum transition taking place on every star, in every galaxy, in every remote corner of the universe, he wrote, is splitting our local world on Earth into myriads of copies. On this reading, the wave function of the universe, defined over superspace, is the ultimate object, a single state vector containing every branch, every outcome, every version of history, all equally real. Proponents argue that this is the most economical reading of quantum mechanics because it removes the mysterious collapse and keeps only the wave function. I state the claim. I do not yet weigh it. And there is a fourth idea, the most radical of all, and it takes the strangeness of the Wheeler-DeWitt equation utterly at face value. The British physicist Julian Barbour looked at the equation's most disturbing feature, that it contains no time variable, that, taken literally, it describes a frozen, static wave function over superspace, and concluded that time is not real. In his framework, which he calls Platonia, reality is precisely the timeless configuration space, a vast, motionless arena of all possible nows, every instant existing at once, with no genuine flow connecting them. The overwhelming human sense that time passes, Barbour proposes, arises because certain configurations, which he calls time capsules, contain within themselves the appearance of records, of memory, of a past. We feel time because each now is structured to look as if it followed from another. It is a breathtaking proposal, and to his great credit as an honest thinker, Barbour does not oversell the mechanism. Writing of his central conjecture that the wave function of our universe should concentrate on these time capsules, he admitted in his own words that he could fill up pages with hand-waving arguments for why this should be so. Remember that admission. When we return to Platonia in the final movement, that phrase, hand-waving, will matter a great deal. I have now placed 4 large claims before you. Creation from a no-boundary state, tunneling from nothing, splitting into many worlds, and a timeless Platonia where the universe simply is. Notice that I have not endorsed or refuted a single one. That restraint is deliberate, and it is the discipline this kind of inquiry demands. For now they are exhibits, laid on the table, awaiting examination. Before we reach that examination, 2 more pieces of the landscape must be set in place. One challenges superspace from within physics, and one, remarkably, has brought the disavowed equation roaring back to life. The challenge from within comes from loop quantum gravity. Where Wheeler's superspace is a smooth continuum of metrics, an unbroken landscape of geometries shading into one another, loop quantum gravity proposes that space is not a continuum at all. The theory was developed from the variables introduced by Abhay Ashtekar and built into a full framework by Carlo Rovelli and Lee Smolin. At the smallest scale, it says, space is woven from discrete threads, structures called spin networks, graphs of nodes and links, where area and volume do not vary smoothly but come in indivisible chunks, the way electric charge comes in whole multiples of the electron's charge. The area operator in this theory has discrete eigenvalues, proportional to the square root of a quantity j times j plus 1 in units of the Planck area. There is a smallest possible area. There is a smallest possible volume. And this discreteness, its advocates point out, automatically cures some of the pathologies of superspace, the conical singularities, the ill-defined continuum, the infinities, because at bottom there is no continuum to misbehave. It is also worth being precise about what superspace is and is not, because it is often confused with a superficially similar idea, the so-called landscape of string theory. They sound alike. They are profoundly different. Superspace is a configuration space within a single theory, general relativity. Its points are the possible shapes of space that one theory permits. The string landscape, by contrast, is a solution space of distinct vacua belonging to a larger theory. The roughly 10 to the 500 different ways, by common estimate, that the extra dimensions of string theory can be folded up, each fold yielding a universe with different physical constants. One is the space of shapes a single universe can take. The other is the space of different rulebooks entire universes might obey. The distinction will matter when we examine how each has been pressed into service against the appearance of design. Keep them separate. Superspace, shapes within one law; landscape, many laws. Now for the resurrection, and for the one place where this entire abstract edifice touches hard, measured reality. The ADM formalism, the 3+1 slicing of space-time that gave birth to superspace, is not merely a philosophical device. It is the working engine of an entire field called numerical relativity, in which supercomputers take Einstein's equations, slice space-time into millions of 3 geometries, and evolve them forward, slice by slice, to simulate what happens when, for instance, 2 black holes spiral together and merge. This is the ADM foliation, made of silicon and electricity, grinding through the geometry of space one slice at a time. And on the 14th of September 2015, at 50 minutes and 45 seconds past 9 in the morning, universal time, that machinery met the universe. The Laser Interferometer Gravitational Wave Observatory, LIGO, recorded a signal designated GW150914. The gravitational waves from 2 black holes, one about 36 times the mass of the Sun and the other about 29, spiraling together and merging into a single black hole of about 62 solar masses, roughly 1.3 billion light-years away. To put that distance in planar units, it is about 7.6 times 10 to the 21st miles, a number with no human meaning except that the wave had been travelling toward us for well over 1 billion years before it arrived. The signal lasted about 0.2 of a second in the detector's sensitive band, between 35 and 350 cycles per second. It stretched and squeezed space itself by a fraction of around 1 part in 10 to the 21, a distortion smaller than 1,000th of the width of a proton across the detector's 4-kilometer arms. It reached the Livingston detector in Louisiana about 7,000ths of a second before it reached the Hanford detector in Washington state. The combined statistical significance was over 5 standard deviations, the gold standard of discovery. Here is why GW 150914 belongs in this story. The shape of that signal, the precise rising chirp of the merging black holes, was computed by numerical relativity, by the ADM 3+1 machinery, evolving the geometry of 2 colliding black holes slice by slice through superspace. The published analysis notes that the numerically computed waveform was confirmed to within 0.1% by an independent calculation. The slicing of space-time that Arnowit, Deser and Meissner devised to make gravity quantizable, the slicing that turned histories into paths through superspace, turned out to be the very tool that let us hear 2 black holes collide 1 billion light-years away. The arena is abstract. The vindication of its foundation is as concrete as a number on a detector readout. What does it mean that an idea invented to tame the mathematics of quantum gravity became the instrument through which we first heard the dark collisions of black holes? It means that superspace, whatever its troubles, is not idle metaphysics. Its skeleton holds up the most precise measurements humanity has ever made. And then there is the strangest turn of all. The Wheeler-DeWitt Equation, disavowed, called intractable, widely regarded as a dead end, has in the last few years come back from the dead in the most fashionable corner of theoretical physics: holography, the study of how a universe's interior can be encoded on its boundary. Researchers have found the Wheeler-DeWitt Equation reappearing in the structure of the holographic correspondence, in a region of space-time now called the Wheeler-DeWitt patch, and in proposals that the complexity of a quantum state is measured by the gravitational action evaluated over exactly that patch. There are new frameworks: Cauchy's slice holography, holography derived directly from the Wheeler-DeWitt equation, and arguments by physicists such as Don Marolf and Netta Engelhardt linking the deepest properties of holography back to the diffeomorphism invariance we flagged at the very beginning: the insistence that only the shape of space matters and not the coordinates drawn upon it. The equation that one of its own fathers wanted thrown into the dustbin of history is now being mined for clues about the deepest structure of reality. What does it mean that the discarded master equation keeps returning? Perhaps that it captured something true, even if no one has ever fully understood what. We have now built the arena, populated it with its great claims, and seen both its triumph and its troubles. Everything to this point I have presented in the neutral voice of a reporter, laying out what exists. That voice now changes, because under all of this elegance there has been, from the beginning, a crack, a single unanswered question that the founders saw, that the critics sharpened, and that the framework has never closed. It is time to stop describing and start examining. It is time to ask where the time went. Return to the supermetric and to the seed I asked you to plant. The Wheeler-DeWitt equation has the form of a wave equation, and in a wave equation, the direction carrying the opposite sign plays the role of time. But in superspace, that direction is not time. It is the size of the universe. There is no separate time variable anywhere in the equation. H hat psi equals 0, and there is no term that says how psi changes from one moment to the next, because there is no moment to the next. The wave function of the universe simply is. Static. Frozen. Taken at face value, the master equation of quantum cosmology says that nothing, anywhere, ever happens. This is the problem of time, and it is not a minor technical wrinkle. It is the fracture that runs through the entire foundation. Here is the heart of it. In quantum mechanics, time is sacred and external, a steady parameter ticking outside the system, against which all change is measured. The Schrödinger equation tells you how the wave function changes as time flows. But in general relativity, time is not external at all. Time is part of the geometry, woven into the very space-time that is supposed to be the thing evolving. When you quantize gravity, you try to make geometry itself into the quantum system. And then, the time you needed as your external clock is swallowed into the geometry you are quantizing. The clock is now one of the things in the box. There is nothing left outside to measure change against. The result is the frozen formalism, an equation for the whole universe in which time has vanished. The physicist who anatomized this problem most rigorously was the Czech-American relativist Karel Kuchar, and his assessment is sober and devastating. In his major review of the subject, he wrote, "In canonical quantization of gravity, the state functional does not seem to depend on time. This hampers the physical interpretation of quantum gravity." He then, in his own words, critically examined 10 major attempts to circumvent this problem and discussed their shortcomings. 10 attempts, not one of which, in his judgment, succeeded in restoring a consistent notion of time to quantum gravity. Think about what that means. The single most basic feature of physical reality, that things happen, that there is a before and an after, cannot be cleanly recovered from the equation meant to describe the quantum universe. This is the part that stays with me when I sit with this subject. Not the infinite dimensions, not the exotic geometries. It is that the equation forgot time, and 60 years of brilliant effort has not found where it went. And now the disavowal, which I promised at the very beginning and which lands with full weight only here. Bryce DeWitt, the man who wrote the 1967 paper, the man whose name the equation bears, turned against his own creation. The physicist Carlo Rovelli, surveying the history, titled his account of the equation with a phrase that says it all. It was disavowed by one of its fathers. DeWitt referred to it as that damn equation and made no effort to hide his unhappiness with it. He said that even at the time, his heart was not really in it. And, in remarks reported from his later years, he judged that the equation should be confined to the dustbin of history, and that it could not serve as the definition of quantum gravity. There is also a quiet historical irony worth recording. The physicist Peter Bergman had developed the same kind of constraint quantization years earlier and disputed the very naming, writing to Wheeler that he had proposed doing this in 1950, several years before DeWitt entered the field full-time. The equation's authorship was contested. Its central concept of time was missing, and the father, whose name it carries, wanted it discarded. There is a small, almost poignant detail in how the equation even came to carry the name it carries. The ideas were thrashed out over years. In the lecture halls of Les Ouches in the French Alps in 1963, where Wheeler and DeWitt argued the canonical theory face to face. Then, in the dense pages of the 1967 paper. And not until a meeting at Osgood Hill in 1988 did DeWitt finally formally accept that the equation would bear his name alongside Wheeler's. 21 years passed between the equation's publication and its author's grudging acceptance of the title now fixed to it forever. Think about what that delay means. A physicist does not take 2 decades to accept the naming of a result he is proud of. The reluctance was there from the beginning, woven into the history. And it tells you something the clean mathematics on the page never could. The man closest to the equation trusted it least. I lay this out not to mock the science. These were serious people doing some of the hardest work in the history of some physics, and I treat their struggle with respect. I lay it out because of a specific argument that is often built on top of this framework, and that argument does not deserve the same respect. The argument is this: that quantum cosmology has shown the universe can come from nothing, with no cause and no creator required. Let us take that claim, give it its strongest form, and then examine whether it survives. Here is the claim in its most forceful version, as its proponents present it. The no-boundary proposal and the tunneling proposal, defined over superspace, describe a universe that arises without any prior classical state. No preceding matter, no preceding space, no preceding time. The universe on this telling creates itself. The popular form of the argument, advanced by some physicists and best-selling authors, is blunt. Science has explained how something can come from nothing, and so the ancient question, why is there something rather than nothing, has been answered without any need for a creating intelligence. That is the claim. I have stated it fairly, now we examine it. The examination turns on a single word, and the whole argument lives or dies on it. The word is nothing. When the quantum cosmologist says the universe came from nothing, the obvious question is what, precisely, that nothing is. Look at what the calculation actually requires. It requires superspace, the infinite dimensional arena of all possible geometries. It requires the Wheeler-DeWitt Equation governing the wave function across that arena. It requires the DeWitt supermetric with its precise indefinite signature. It requires the laws of quantum mechanics, superposition, amplitudes, the Born rule for turning amplitudes into probabilities. And it requires a specific hand-chosen boundary condition, the no-boundary prescription or the tunneling prescription, to pick out one wave function from the infinitely many the equation permits. Strip all of that away, and there is no calculation, no universe, no creation, none of it. So consider what the nothing of quantum cosmology actually contains. An infinite mathematical arena, a master equation, a metric, the full apparatus of quantum theory, and a chosen rule for boundary conditions. That is not nothing. That is an enormous, intricate, highly specific something. The argument has not produced a universe from nothing. It has produced a universe from superspace, plus the laws of quantum gravity, plus a chosen boundary condition, and then quietly relabeled that rich structure with the word nothing, because the word carries the philosophical conclusion the argument wants to reach. This is the something from nothing rebuttal, and it is decisive. True nothing, the absence of all things, no space, no arena, no law, no equation, no quantum state, no potential, has no causal powers whatever. From true nothing, nothing comes. 0 plus 0 is 0. The moment you have an equation that can be solved to yield a universe, you no longer have nothing. You have a law-governed something. And the only question worth asking is where that something came from. Let me ground this in ordinary experience, and let me be honest about exactly where the analogy breaks, because the breakdown is the point. We speak in everyday life of an entrepreneur who built a company from nothing. We admire it, and we know the instant we examine it that the phrase is a figure of speech. The entrepreneur had a building, or at least a kitchen table, a loan or savings, a market of customers, laws of contract, a working economy, language itself. The nothing was shorthand for without inherited wealth. It was never literal. Now watch where the analogy breaks against the cosmic claim. With the entrepreneur, we all understand that the background, the building, the economy, the laws, was already there, and no one imagines the business explains the existence of the economy it grew within. But the quantum cosmology argument asks us to forget the background entirely, to treat superspace and the Wheeler-DeWitt Equation and the laws of quantum mechanics as if they were the literal nothing, as if they required no explanation, as if the universe they generate accounts for them. The analogy breaks at exactly the point where the claim needs it to hold. The business never explained the economy, and the wave function never explained superspace. That is the flaw, exposed. The argument helps itself to the very structures whose existence is the thing in question. And there is a second blade, sharper still. Set all of that aside and ask only whether the proponents even agree on what the naturalistic origin was. They do not. The no-boundary proposal of Hartle and Hawking and the tunneling proposal of Vilenkin, the two flagship accounts of the universe's quantum origin, contradict each other. They differ, as Vilenkin himself notes, by something as slight as a sign, and yet they predict different things, and their authors have disagreed about which is correct. Worse, a group of physicists, Turok, Feldbrugger and Lehners, have argued that the no-boundary path integral is not even mathematically well defined, that the calculation, done carefully, gives nonsense. So here is the question the confident popularizer cannot answer. Which naturalistic origin of the universe are we being asked to accept in place of a creator? The smooth, no-boundary cap, or the tunneling from nothing? They cannot both be right. One of the field's own founders called the master equation unfit to define the theory. And we are told this disputed, timeless, internally contradictory framework has closed the question of why there is a universe. It has not closed the question. It has not even agreed with itself. What does it mean when a framework offered as the replacement for a creator cannot define time, cannot agree on its own origin story, and was disowned by the man who built it? It means the confident conclusion was never earned by the physics. It was smuggled in on top of it. The verdict on the first claim, then, is clear. The universe did not come from nothing, because the nothing on offer is a structured, law-governed, contingent arena that could have been otherwise, and therefore demands explanation. Something has always existed. The proponents and the theist agree on that much the moment they grant an eternal arena of laws. The only question is what that something is. An unconscious mathematical structure that just happens to exist, fine-tuned and law-bound for no reason at all, or an intelligent cause with the power to ground the arena and the will to select its laws. We will return to which of those the evidence favours. Now the second claim, the most elegant of the four, and in a way the most seductive. It takes the frozen formalism, the very problem of time that haunts the equation, and turns it into a metaphysics. The claim is that time is an illusion, that the universe is a timeless block, a static Platonia of all possible nows, and that because there is no time, there is no beginning, and a thing with no beginning needs no cause and no creator. Julian Barbour is the most serious and honest advocate of this view, and I present it in its strongest form. If the Wheeler-DeWitt equation is taken literally, reality is timeless, and a timeless reality simply is, requiring nothing to bring it into being. Examine it. Grant, for the sake of argument, the entire timeless picture. Grant that Platonia is real and that time is a kind of illusion woven from time capsules. Two problems remain, and neither is small. The first is the one Barbour himself flagged in the admission I asked you to remember. The mechanism that is supposed to make a static block of nows feel like a flowing history, the claim that the wave function concentrates on time capsules, is, in his own honest words, something for which he could fill pages with hand-waving arguments. The keystone of the timeless picture, by the architect's own admission, is not derived. It is hoped for. A worldview cannot rest its rejection of a beginning on a mechanism its own author calls hand-waving. The second problem is deeper, and the everyday mind grasps it instantly. Suppose you remove time entirely. You still have Platonia, a specific, infinite, intricately structured arena of all possible geometries, governed by one particular supermetric, obeying one particular equation. Why this Platonia? Why these laws and not others? Removing time does not make the structure self-explanatory. It does not make it necessary. A timeless thing can still be contingent, still one option among countless others, still demanding an answer to the question, why this one? Picture an immense library containing every book that could ever be written, all existing at once, no time, no reading, just the static totality of all possible texts. Even granting that frozen library exists timelessly, you would still ask, why does this library exist rather than no library? Why these shelves, this architecture, these laws of grammar that make the books coherent? Timelessness silences the question of when it began. It does nothing to silence the question of why it exists, and why in this exact form. The reductio is plain. If removing time removed the need for explanation, then any sufficiently strange reformulation of physics could dissolve the deepest question in metaphysics by definition. That is not an answer. It is an evasion dressed as an answer. The frozen Platonia, far from eliminating a cause, stands revealed as a vast and exquisitely specific artifact. And artifacts of that precision point beyond themselves. The third claim moves from the origin of the universe to the appearance of design, and it leans on the many worlds reading we met earlier. The claim is that fine-tuning is an illusion of perspective. If the universal wave function contains every branch, every outcome, then somewhere in the vast tree of worlds, there will be branches where the conditions happen to permit life. And of course, we find ourselves in one of those, because there is no one in the lifeless branches to notice. Design dissolves into selection. I give the argument its due. It is internally coherent, and it follows from taking the universal wave function literally, which is exactly what the Wheeler-DeWitt framework invites. But examine what it actually explains, and what it quietly leaves untouched. The many worlds branches all obey the same underlying laws, the same Wheeler-DeWitt equation, the same supermetric, the same fundamental constants written into the structure of the theory. Branching produces different outcomes within a fixed set of laws. It does not produce different laws. So even if every quantum outcome is realized in some branch, the deep question, why are the underlying laws themselves life-permitting, is not answered at all. The fine-tuning of the constants is a property of the rulebook, and every branch shares the rulebook. Many worlds explains why we observe a life-permitting outcome given life-permitting laws. It says precisely nothing about why the laws are life-permitting in the first place. The hard problem is untouched. And here the inversion writes itself. The materialist often accuses the theist of extravagance, of invoking an unseen, unmeasurable being to explain the world. Look then at what is being proposed in its place. Not one unseen entity, but an unbounded infinity of unseen, unmeasurable, in principle undetectable universes, postulated for the express purpose of making design look unnecessary. Every quantum event, DeWitt wrote, splits our world into myriads of copies. And we are asked to accept this endless, invisible proliferation as the economical, scientific alternative to a single intelligent cause. By any honest accounting, that is not parsimony. It is the most extravagant ontology ever proposed, summoned precisely to avoid a conclusion. Strip away the mathematics and ask the plain question. Is it more reasonable to believe in one mind behind a fine-tuned universe, or in infinitely many unseeable universes invented so that the fine-tuning can be called an accident? Before I continue, sit with that comparison honestly. Which is the leaner hypothesis? The fourth claim is the multiverse argument's other form, the string landscape. And it brings us at last to the numbers, which I have deliberately saved for this moment. The claim is that the roughly 10 to the 500 possible vacua of string theory form a vast landscape of universes with different constants, and that we simply inhabit one of the rare vacua where the constants permit life. Fine-tuning, again, dissolved into selection across a multitude. Examine the structure of this move. The landscape is not observed. No other vacuum has ever been detected. The theory carries a notorious measure problem. No agreed way to assign probabilities across the multitude, which means it makes no sharp predictions. By the ordinary standards of science, an untestable multitude invoked to explain away an observation is not an explanation. It is a philosophical preference wearing the costume of physics. But set even that aside and confront the fine-tuning itself, because the numbers are what make this more than a debate about taste. Consider the cosmological constant, the energy of empty space. When physicists calculate what the quantum vacuum should weigh, the theoretical prediction exceeds the observed value by a factor of around 10 to the 120. That is not a small discrepancy. Written out, it is a 1 followed by 120 zeros. For the universe to permit galaxies, stars, and life, the contributions to the vacuum energy must cancel against one another to leave a residue smaller than the prediction by that staggering factor. A balance, as the physicist Steven Weinberg framed it, of about 1 part in 10 to the 120. I want to be careful and fair here because honesty is the whole point of this examination. This is a cancellation among large independent contributions, not a single theory contradicting a single measurement. And some physicists argue about how the fine-tuning should be counted. But no serious party disputes the precision of the balance the universe actually exhibits. Think about that number for a moment. 1 part in 10 to the 120. If you adjusted the vacuum energy by a fraction far smaller than that, the universe either flies apart before a single galaxy can form, or collapses back on itself in an instant. The dial sits at exactly the value that permits a cosmos. What does it mean that the most basic energy of empty space is balanced on an edge that fine? And the cosmological constant is the gentle example. Roger Penrose examined not the constants, but the initial state of the universe, its extraordinarily low entropy at the beginning, the precise smoothness that allowed an ordered cosmos to unfold rather than a chaotic mess, and calculated the precision required. His result is a number that breaks the mind. To set the universe in its special initial state, he wrote, the target is an absurdly tiny volume of the phase space of possible universes, about 1 part in 10 raised to the power 10, raised again to the power 123. That is not 10 to the 123. It is 10 to the power of a number that is itself 10 followed by 123 zeros. Penrose pointed out that you could not even write this number down in ordinary decimal form. If you placed a single zero on every fundamental particle in the observable universe, you would still run out of particles long before you ran out of zeros. And note the word Penrose himself reached for, an atheist mathematician describing the precision required. He wrote of what the Creator must do to aim for so tiny a target. I will be fair once more. Penrose intended the word loosely, and other physicists, such as Sean Carroll, argue that a low entropy beginning is not by itself tuning for life. Note the disagreement. And then note what no one disputes: the precision itself. 1 part in 10 to the 10 to the 123. That is the dial setting of the early universe. Now bring the prosecution to its point. The landscape and the many worlds and the no boundary nothing, every one of these moves is offered to make precision like this look unremarkable, to dissolve it into selection or accident or perspective. But none of them removes the precision. They relocate it. The landscape relocates the fine-tuning into an untestable meta-theory, whose own measure no one can compute. Many worlds relocates it into laws that every branch still shares. The from-nothing proposals relocate it into a structured arena they mislabel as nothing. The precision is conserved. It cannot be argued away. It can only be moved somewhere harder to see. And precision of this magnitude, a dial set to 1 part in 10 to the 120, an initial state targeted to 1 part in 10 to the 10 to the 123, is the signature of one thing in all of human experience. Precision requires decision. A value selected against overwhelming odds from a continuum of alternatives is the fingerprint of a choice. And a choice requires a chooser, something with the knowledge to know which value permits a cosmos, the power to set it, and the will to do so. Follow that conclusion where it leads, the way an honest investigator follows evidence. Whatever configured the arena of superspace and selected the laws that govern it, and tuned the constants to their razor's edge values, must have existed independently of the universe it produced, beyond its space, beyond its time, beyond the very arena whose existence is in question. It must possess power beyond the physical, because it grounds the physical. It must possess knowledge beyond comprehension, because values it selected are precise beyond comprehension. And it must possess will, because, out of infinite alternatives, a particular configuration was chosen. Power, knowledge, will. These are not the attributes of an equation or a metric or a configuration space. They are the attributes of a mind. The evidence, examined honestly and without flinching, does not point to an unconscious mathematical accident. It points to an intelligent cause. There is one last thread, and it belongs to Wheeler himself, the man who named Superspace. Late in his life, Wheeler's thought turned from geometry to information, from it to bit, as he put it. The idea that the foundation of physics might be not matter but information, and that the act of observation might be woven into the fabric of reality. He spoke of a participatory universe, in which observers are not incidental latecomers, but somehow part of how reality comes to be definite. And the idea cost him. He wrote in something like anguish, "Each of us a private universe? Preposterous!" recoiling from where his own logic seemed to lead. I do not present Wheeler's participatory universe as proof of anything. It is speculative, and he knew it. But I note the shape of it, because it is suggestive. The framework keeps reaching for the observer, for mind, for information, as if the unconscious geometry it started with were not quite enough to close the circle. Materialism keeps needing the very thing it cannot explain, the conscious observer, standing outside the equation, for whom any of this means anything at all. The deepest physics of the last century kept circling back to mind. That too is part of the evidence file. So let us gather the whole case before we close. The framework cannot define time. Its founding equation was disavowed by the man who built it. Its nothing is a structured, contingent arena. Its competing origin stories contradict each other. Its multiverses are untestable, and its many worlds leave the laws untouched. And through every one of these moves, the fine-tuning of the universe to 1 part in 10 to the 120, and to 1 part in 10 to the 10 to the 123, survives, undiminished, refusing to be explained away. 60 years of the most brilliant effort in the history of physics has produced a magnificent arena and a magnificent equation, and has left the deepest questions exactly where they have always stood. Why is there something rather than nothing? Why these laws? Why this precision? The honest answer is that the science describes the how with breathtaking power and cannot touch the why at all. And where the why has an answer, the evidence points in one direction. Let me bring this exploration to a close. We began with a single point that was an entire universe and an arena, superspace, large enough to hold every shape that space could ever take, infinite in its dimensions, where a whole cosmic history is only a curve. We watched John Wheeler reach for that arena, and watched Arnowit, Deser and Meissner slice space-time into the 3 geometries that fill it. The same slicing that, decades later, let humanity hear 2 black holes collide 1 billion light-years away. We followed Bryce DeWitt as he wrote the master equation of that arena, the Wheeler-DeWitt Equation, the wave function of the universe set equal to a constraint. The right-hand side, a stark and forced 0. And we watched him come, over a lifetime, to call it that damned equation and ask for it to be discarded. We met the strangeness it carries, the supermetric whose one special direction is not time but size, the conical singularities where the most symmetric universes balance on a knife edge, the timeless Platonia that takes the frozen equation at its literal word. And we confronted the problem of time, the fracture that no amount of brilliance has closed, the equation that forgot how anything ever happens. Then we tested the claims built upon all of this, that the universe came from nothing, when the nothing was an infinite arena, a master equation, and a hand-chosen law. That time is an illusion, and so no beginning is needed, when the timeless arena is itself a specific contingent artifact, its keystone admitted to be hand-waving. That the multiverse and the many worlds dissolve design, when the fine-tuning only relocates, never vanishing, the dial of the vacuum still set to 1 part in 10 to the 120, the initial state still targeted to 1 part in 10 to the 10 to the 123. The precision is conserved. It cannot be argued away. And precision in all of human experience is the residue of decision. This is the rational conclusion, and I do not hold it tentatively. The arena of superspace is real and beautiful and contingent. The laws that govern it could have been otherwise. The constants were set with a precision that has no name in human language. Something configured this, something beyond space and time, possessing power, knowledge, and will. The science has described the machinery of the cosmos with a depth our ancestors could not have dreamed. It has not explained, and by its own nature cannot explain, why the machinery exists at all, or why it was tuned so exactly for a universe that could hold minds able to ask the question. The honest investigator, following the evidence and refusing to flinch, arrives at an intelligent cause, not as a retreat from physics, as the conclusion physics keeps pointing toward and cannot itself contain. If you found value in this exploration, consider subscribing. It helps these deep dives reach more curious minds. And there is a thread I left deliberately half open tonight. We touched the idea that time itself may be an illusion, that the universe could be a single frozen stack of nows, every moment existing at once, the flow we feel only a trick of memory. I barely stepped through that door here. If it unsettled you, if some part of you needs to know whether the present moment is the only real one, or merely one shelf in a timeless library, I have followed that question much further elsewhere. You will find where on the end screen now and waiting in the description. Wheeler asked one question as a child, standing at the edge of a bathtub, that he chased for 70 years and never fully answered. What happens when you get to the end of things? He built Superspace looking for the answer. He found an infinite arena, a frozen equation, and, at the end of his long search, a mystery deeper than the one he started with. Perhaps that is the truest thing this story has to teach. The arena must be a larger object, Wheeler said. And it is. Larger than space, larger than time, larger than the equation built to rule it, large enough that, standing inside it tonight, on one frozen point among infinitely many, you can look out at a universe tuned past all accident and recognize, in the silence where time should be, the signature of a mind. Good night.